let's talk about capacitors, what they are, how you use them. So, the book definition of a capacitor, I suppose, is a device which stores electric charge. And what is electric charge? It's essentially a bunch of electrons all bundled together, and you experience electric charge when um, you walk across the carpet, touch the doorknob, and get shocked. So that's a bunch of electrons all bundled together, and so you would say that as you walk across the carpet, build up electric charge. Okay, so in a way, you actually have become a capacitor. But we can do better than that. There are capacitors which can store far more electric charge than you, so that's a good thing. Essentially, you can conceptualize a capacitor as two pieces of conductor, two plates of conductor perhaps, that are very close, but they're not touching. And sometimes, in order to get even closer, let me draw. Let's see. I'll use a pencil. They'll put a little sheet of material between it to isolate the two, so they can actually squash the two conductors together. All right. So why do we want to have two conductors in this sort of format? And then, well, we'll solder wires to both ends, and then we might put a battery here and charge it up. So what's going to happen is, okay, well, the first thing we have to talk about actually is something called conventional current. So we know that physically electrons are the subatomic particles that are moving around, that compose electricity. But for whatever reason, for simplicity or for making it easier to making circuits easier to reason about, perhaps, we've chosen conventional current to say that a positive electricity carrier flows from the positive terminal of the battery to negative. So that's how, I guess I've decided that's how I'm going to explain it, even though it really is electrons. So yeah, let's do this. We're going to say that protons come out of the battery, which they don't, they're electrons coming out from the other side, but conventional current, all right? Protons come out of the battery, and they will start to populate this side, this conductor, but they can't reach over here because even though they're very close, they're not touching, and electricity can't jump a gap unless it's got some help, and that's also what this insulator is there for. Okay, so without it, if it was a small enough gap, the protons would be able to jump across the gap. We don't want that. It won't be able to store charge anymore. So we have this insulator going between. And then eventually, let's say this was 12 volts, just because eventually we'll see that this plate has become equally charged so that there is 12 volts across that you would read with a voltmeter from one plate to the other. There's 12 volts. Okay, and at that point you could disconnect the battery and connect your voltmeter. That's my voltmeter. And you should read 12 volts. As you're reading 12 volts, you'll see it start to drop down because the voltmeter is going to dissipate some of that charge through its own measuring circuits, and we can actually see this. So this is my first demo I'm going to set up. This is a electrolytic capacitor rated for 47 microfarads. A farad, named after Faraday. Let's go to volts DC. Farad is the standard unit for measuring capacitance. Okay, so this is not 12 volts. This is not even 5 volts right now because my battery is charging. We will first check and see what it is. 3 volts. Alright, so there's 3 volts. Now, electrolytic capacitors do have a positive and negative that you have to be careful about. So the way that they're constructed, they only work properly whenever you put the negative where the large arrows are pointing to where negative is. You can see that. Saying negative is this way, so that's what we will do. And I'm just going to touch for a moment, okay? And now we're going to measure the voltage. You'll have to watch it quick because, okay, I probably waited too long. It was already less than a volt. Let's do it again. Okay, 1.3. We caught it a little earlier. But you can see this thing is storing voltage. Why is the number dropping? Well, some of the stored charge is leaking out as current through the voltmeter just a little bit, but it's enough that as you wait, the voltage drops. But that goes to demonstrate that electric charge can be stored in a capacitor in that manner. So, once you have the capacitor charged up, then nothing else happens until you, until the capacitor is able to discharge on something, which is, I mean, we showed that just connecting the meter to it was enough for it to start to discharge. But in ideally, if you were to charge up a capacitor and not measure it, it would sit at whatever voltage you charged it to indefinitely. But that won't happen because it's the real world, and we'll have, you know, things just kind of leaking off and dissipating. So, and if you measure it, that will drop the voltage even more. So here we go. Let's try to harness some of the power stored in a capacitor. We're going to build a similar circuit where I'm going to have a, doesn't matter voltage really, but we'll say that's a 3-volt battery, DC supply into a capacitor. I drew it smaller. This is actually the standard symbol of a capacitor in a schematic. It looks a little like a battery, but a battery is a series of long and short lines. So they can be confused. It's important that you show that they're the same length to make it look different from the battery symbol. Okay, and well, you know what, I didn't draw it, but let's say that's a switch there, okay? And also we have another switch. This one's open, going into a resistor, which is a load device. Whenever we close this switch here, what will happen is the same thing I did with the demo. It will charge up the capacitor until the voltage across it is 3 volts. And this side will be positive compared to this side. All right? And then we will close we will open the switch, and the capacitor should stay at 3 volts. It's already been charged up. It's disconnected from the battery at that point. Then we will close this switch here, and then current will flow, conventional current will flow from positive of the capacitor back to the negative. Why? Because these they're electrons really, but in our conventional model, they're protons that are super close to this other side, and they don't all want to be clustered up here. They they're attracted to, you would say that they're attracted to this side because it has a large difference in charge, and all of those protons don't want to be clustered up there. They want to spread out. And it's kind of the idea driving what voltage is. If you have 100 volts, then that's like a lot of charge in one place and a little bit of charge in another place, and it all wants to rush in and equalize. That's what we call it potential difference. So that's why the current will flow as it does. It's conventional current, of course. And this resistor will determine how much current, okay? So if we set this to something fairly large, I happen to have a 47K ohm resistor, then it will take longer for the capacitor to discharge. And if we set it to something really small, then it will discharge in an instant. So we can control this. How long will it take? It's governed by the Euler's number, I believe, or E. Okay, it's the inverse of the natural log function. And this is the voltage from the instant that you connect the load. The voltage at any given time will be equal to the original voltage times e to the negative time over, we have this guy that looks like a capital T, but that's actually tau. It's the time constant, which is equal to this is R, the resistor, the value of the resistor, 47K, whatever, times C, which is the capacitance in farads. That's tau. Like I said, this is times the original voltage. So, real quick, let's say that one time constant has passed, or T over tau is equal to 1. That's not necessarily 1 second. You would have to multiply 47K by whatever capacitor you have to get that. So let's do it. One tau has passed, then that would be, if our supply voltage is, well, you know what, I won't even multiply by, we'll just see what it would be as a percentage. So -1, here's how my calculator does it. There's the e to the x button. So it's saying that at that time the voltage would be 36.8% of the original voltage. That's after one time constant has passed. Now this is interesting because it's somewhat counterintuitive. You might think a time constant is how long it takes for the capacitor to discharge. It's not. It actually is going to take several time constants before the capacitor is discharged. Actually, the capacitor never gets fully discharged because as the protons are going through the circuit, the potential difference is decreasing, the voltage across the capacitor therefore is decreasing, and so the protons are less attracted to the other side and the current drops. Fewer of them are moving around and it never really stops. It eventually gets so small that you would say that it has stopped, but well, we can do this, or we can play with it. Let's say that 4 time constants have passed. Well, we did 1. I guess we'll do 2. So 2 time constants, you'll have about 14% of the original voltage. 3 time constants, 5%. So, you know what? For your design, that might be acceptable to say that by the time that T is equal to 3RC, then 95% of the capacitor will be 95% discharged. And for your design, that might be fine. If you wanted to wait another time constant, go for it. Then you'll have 1.8% of the original voltage. So we could do an example with the numbers that I have up here, and I have, like this guy I showed, is a 47 microfarad capacitor. Microfarad. 1 farad is a huge amount of capacitance, actually. So we'll calculate tau. That'll be 47,000 ohms times 47. What was 74? 47 times 10 to the negative 6, because that's what micro is. Micro is a millionth. And we get 2.209, and that's, the unit on this is seconds. So if we waited 2.209 seconds, that means we've waited 1 tau, 1 time constant, and it will be, well, that's what we put through the first time. 1 time constant is 36.8% discharged. So I don't have a real good way to show this visually. That's something that could be done on an oscilloscope. Maybe I'll show that in another video. But as you can see, capacitors are fairly simple in function, but they can become somewhat complex in the math that goes into it. And see if we want to go there. I was going to go into how capacitors work in an AC alternating current circuit, but the time on this video is getting pretty long, so I'm going to cut it short, and I'll have to touch on that later. Anyway, thank you for watching this video on capacitors. If you have any questions, leave them in the comments. I'll do my best to answer them. Otherwise, thanks for watching. Bye.